here. Each time I took this general formula and made n bigger and bigger and bigger, the amount went up, but the amount went up, less and less each time I did so. So when I look at the same formula, now I'm going to let P, R, and T all equal 1. The only thing I'm going to be changing is N. Okay? So we have an initial amount of 1. I'm going to be multiplying a multiple that's going to be a growth, 1 plus R over N, where R is 1, N is going to be these numbers over here that kind of represent the same kind of numbers we talked about before. I'm going to plug it into that formula here. Each time I do, A keeps going up, but it starts leveling off a bit. And if I keep going and going and going until like N becomes infinitely large, this 2.718 blah 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 number, seems to be what it's like, leveling off to be. So as N approaches infinity, A approaches that 2.718282 blah 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 value, and that's a value we call E, and that's the other exponential base that we've talked about earlier in video 1, but we didn't talk a whole lot about what it was and where it came from. So we did this growth here, but E does show up in many other instances, and we actually do have formulas, that center around E for exponential growth and decay. Whether I use E as my base or I use another base, A, which would be many different values, doesn't matter. I should get the same results. The only thing that when we use the exponential base E is that we're assuming that that if we have a growth or decay, that growth is occurring at a constantly over a period of time, and that's what we're going to be using. Because again, when I'm asked to, you're going to see a term that's going to say I'm compounding continuously. You're not going to usually find any kind of bank account or anything that compounds your interest continuously, because the premise itself is kind of hard to do. I'm going to take your interest rate, split it into an infinite number of infinitely small pieces, and apply it an infinite number of times. We could figure out what that is approximately, what that would be, and that would also represent the maximum amount you would get from an interest rate and the starting amount from compounding only. You know, so when you see the term though, compounded continuously, we don't use the formula we had on the previous page that A equals P times the quantity 1 plus R over N to the NT power. It changes to this: A equals P times E to the RT power, where again R is going to be A is still the final amount after a period of time T, which is typically in years. P is still the initial amount. E is our exponential constant, that 2.718 yada yada yada. R is still going to be the interest rate written as a decimal. So if you're given the same circumstance we started with in example 15 and are told that we're going to take $5,000 with a 6.9% annual percentage rate, how much will it be worth after 10 years if the interest is compounded continuously? I'm going to use this second formula, and that's the only time I use this second formula for compound interest. So I plug those things in, and when I plug it in, I get $9,968.58, which wasn't much bigger than what I had when I had it compounded hourly. But this represents the maximum amount of money I can get off of an account with 6.9% annual percentage rate with a $5,000 initial investment, no other deposits being made. That's the maximum I could get just by changing the number of times I compound only.